All right, good morning, everybody. This is Algebra Lesson 7. Are there any questions about homework problems or anything that we did on Monday? No questions? Okay. So we were talking about permutations on Monday, and let me just do a little calculation. So a permutation of a set X is a function from the set to itself that is 1-to-1 and onto. And the set X can be any set, finite, infinite. If X is the set of the first n positive integers, then Sn is the set of permutations, which is a group, and it is called the symmetric group. So this is one of the fundamental non-abelian groups in mathematics. The permutations, or we can think of this as the symmetries of a set X. So let me just do an explicit calculation. Suppose I take n equal to 3. So S3 is the set of all functions from 1, 2, 3 to 1, 2, 3 that are 1-to-1 and onto. And a standard way to write a permutation is as a 2-row matrix. I put 1, 2, 3 in the first row, and wherever 1, 2, 3 goes under sigma, sigma of 1, sigma of 2, sigma of 3. That's the standard way to write a permutation. So for example, if I let sigma be this permutation, this means sigma is the function which sends sigma of 1 to 2, sigma of 2 to 3, and sigma of 3 back to 1. And you can actually draw a kind of a picture of this. It's like 1 gets sent to 2, 2 gets sent to 3, 3 gets sent back to 1. So we have a kind of a cycle. So let's list all the permutations in S3. So S3 can send, well, first of all, there's always the identity permutation that sends 1-to-1, 2-to-2, and 3-to-3. It sends everything to itself. We have the permutation sigma that I just wrote down, 1-to-2, 2-to-3, 3-to-1. If we iterate this, if we look at sigma squared, that means sigma followed by sigma. Sigma sends 1 to 2, and you apply sigma again, 2 goes to 3, so 1 ends up at 3. Sigma sends 2 to 3, and then sigma again sends 3 to 1, so 2 ends up at 1. Sigma sends 3 to 1, so sigma squared, 3 goes to 1, 1 goes to 2, it ends up at 2. So that's sigma squared. And we also have some other permutations. we have tau 1. Let's say tau 1 fixes 1, but interchanges 2 and 3. Tau 2 sends 2 to 2, but it interchanges 1 and 3. And tau 3 sends 3 to 3 and interchanges 2 and 1. So we have at least these 6 permutations in S3, and that's all there are, because it's,
Oh,
is there a question?
yes. Can you hear me?
Yeah, go ahead.
Okay. So for the sigma squared, so basically what I'm getting at is you would just do the mapping twice. So normally for the regular sigma, it would just be 1 to 2, but then you would just do it again, and then 2 ends up at 3, if I'm looking at it correctly, right? You
Yeah.
just do it twice.
Because multiplication of permutations is composition of functions. So sigma squared is sigma composed with sigma.
Okay, yeah, I see.
That's what, all right. So a permutation is a function, and the multiplication, the binary operation in this group of permutations is functional composition. Just like in calculus, you took composite functions, you differentiated them with the chain rule if you had to, and so on. Just composition of functions, which you use in calculus all the time. And the only thing is in algebra, it's easier because the functions are much simpler. So a theorem about permutations on the symmetric group says that Sn, when you put absolute value signs a set, this means the number of elements in the set is always n factorial, which means the product of all the positive integers up to n. Right, so I claim this is true for all n. So the proof, let's see if we can prove this. The proof might be, we can prove by induction on n. So if n equals 1, what is the set S1? Well, this is just all permutations of a set with one element. There's only one thing you can do. 1 goes to 1. That's the only permutation of a set with one element. That's the identity. What about n equals 2? So in the standard form of writing this, 1 goes to 1. There's no other possibility. What about permutations of the set 1, 2? You can have the identity. And the only other possibility is if 1 doesn't go to 1, 1 has to go to 2, but then 2 has to go to 1. So S1 just consists of these 2 permutations. Sorry, S1 is just the identity. So the cardinality is 1, which is 1 factorial. There are 2 permutations in S2, 2, which is the same as 2 times 1 or 2 factorial. So this statement is true at least for n equal 1 and n equal 2. So let's assume the statement is true for n. That is, if you take a set, not just of the integers from 1 to n, but any set with n elements, the number of permutations is n factorial. And now we take a set with n plus 1 elements. I say the integers from 1 up to n plus 1. So how do we count the number of permutations of this? So suppose we let sigma be some permutation in this set. So in particular, we can divide the permutations up depending on where n plus 1 gets sent to. So Sn plus 1, you can look at all permutations where S of n plus 1 is equal to some number A between 1 and n, and take the union of this as A goes from 1 to n plus 1. So if you have all the permutations of this set, they match each element to a different element. Fix n plus 1, it might be sent to 1 or to 2 or to 3 or to itself. So this is a partition of the set of permutations. Every permutation sends n plus 1 to some number A. For each A, look at all the permutations that send n plus 1 to A, and n plus Sn plus 1 is the union of these sets. So this is a partition of Sn plus 1. A partition means you break a set up into pieces that have no elements in common. So let me just write this down again. Sn plus 1 is the union for all A from 1 up to n plus 1. All permutations in Sn plus 1 where sigma of n plus 1 is equal to A. Now, let's look at one of these sets. So fix A. How many functions, permutations, are in the set of sigma, which sends sigma of n plus 1 to A? So let's say a function, I don't know, let me call this something. I'll call this x of A. So a function tau is an xa if and only if tau sends the first n integers to a set of n integers, the integers up to n plus 1 with A removed. Right? Because if sigma sends n plus 1 to A, then no other element can get mapped to A. So the other n elements, 1 through n, get mapped to a number between 1 and n plus 1, but not A. A is missing. And by the induction hypothesis, this is the way I should state it carefully. If x and y are sets with exactly n elements in each of them, then the number of functions from x to y that are 1 to 1 and on to is n factorial. So each of these sets has n factorial. So the cardinality of the set of all permutations is the sum of the cardinalities of each of these sets and each of these sets has cardinality n factorial. So I'm adding n factorial to itself, n plus 1 times. That's n plus 1 times n factorial, which is exactly n plus 1 factorial. So that is a proof. So in particular, S3, the number of elements in that set is 3 factorial, which is 1 times 2 times 3, which is 6. And I wrote down 6 permutations in that set. So that's all there are. S3 is exactly this. Now, to understand the group, you need to know the multiplication table. So we have E sigma, sigma squared, tau 1, tau 2, tau 3. E sigma, sigma squared, tau 1, tau 2, tau 3. we need to compute the multiplication table. So I will do some of it. It's all written down in the notes, but you need to be able to compute this yourself. What is E times E? Well, E times the identity of, E is the identity, so E times anything is the anything. So E times E is E, E sigma is sigma, E sigma squared, tau 1, tau 2, tau 3. And multiplying on the right by the identity, sigma E is sigma, sigma squared E is sigma squared, and tau 1, tau 2, tau 3. This is a 6 by 6 matrix. I have to fill in 36 entries, and I guess I've done 11. That's not so bad. What is sigma times sigma? Sigma times sigma is sigma squared. What is sigma times sigma squared? Let's calculate that. Sigma times sigma squared, that means of x, of some number x, is sigma of sigma squared of x. That's what composition of functions means. So sigma sigma squared of 1 is sigma of sigma squared of 1. Sigma squared is this. 1 goes to 3. So this is sigma of 3. Sigma was, since 3 to 1, so this is 1. So sigma times sigma squared is 1. Now, this is really an important calculation. You absolutely positively have to understand this, or you won't be able to do anything with groups. Right? So please ask me to explain this if you need more explanation.
Professor, could you repeat?
Okay, so this is the permutation sigma. 1 goes to 2, 2 goes to 3, 3 goes to 1. I already calculated sigma squared when you compose sigma to itself. 1 goes to 3, 2 goes to 1, 3 goes to 2. So this is sigma and this is sigma squared. So what is sigma times sigma squared? All right, I want to compute sigma times sigma squared. It's a group. In a group, you can multiply. So how do I multiply these two permutations? Well, the multiplication operation is composition of functions. So sigma times sigma squared, this is the composite. So sigma sigma squared of 1, this means sigma applied to the number sigma squared of 1. Sigma squared of 1 is 3. So this is sigma of 3. Sigma of 3 is 1. So 1. So sigma sigma squared of 1, 1 goes to 1. Okay, questions about this? What's sigma times sigma squared of 2? This means sigma applied to the number sigma squared of 2. Sigma squared of 2 is 1. So this is sigma of 1. Sigma of 1 is 2. So 2 goes to 2. What is sigma sigma squared of 3? This is sigma of sigma squared of 3. Sigma squared of 3 is 2. Sigma of 2 is 3. So 3 goes to 3. So when I multiply sigma and sigma squared, I get 1 to 1, 2 to 2, 3 to 3. That's just the identity. So sigma times sigma squared is the identity. And So sigma times sigma squared is the identity. So this is sigma times sigma times sigma, right? Sigma squared is sigma times sigma. By associativity, this is the same as sigma times sigma, which is sigma squared times sigma. So sigma squared times sigma is also the identity. What is sigma squared? What goes in here? Sigma squared times sigma squared. This is sigma squared times sigma times sigma. That's sigma squared sigma times sigma. This is the identity. Identity times sigma is sigma. What's sigma times tau 1? So remember, sigma is this permutation. Tau 1 fixes 1 and interchanges 2 and 3. So what is this composite function? 1 goes to 1, 1 goes to 2. So 1 goes to 1 goes to 2. 2 goes to 3, 3 goes to 1, so 2 ends up at 1. 3 goes to 2, 2 goes back to 3, so 3 goes back to 3. So sigma tau 1 is the permutation that fixes 3 and interchanges 1 and 2. That's what I call tau 3. So sigma tau 1 is tau 3. What is sigma squared tau 1? Sigma squared is 3, 1, 2. Tau 1 fixes 1 and interchanges 3 and 2. So what is the composite? Yeah, is there a question?
Yeah, how did you get the Taiwan?
That's the definition of tau 1. Right. I defined this is tau 1, this is tau 2, this is tau 3. This is the definition of those. I defined these. This is tau 1, this is tau 2, this is tau 3.
Okay, I see now. Thank you.
So tau sigma squared tau 1, you apply tau 1 first. 1 goes to 1 to 3. 2 goes to 3, 3 goes to 2. 3 goes to 2, 2 goes to 1. So sigma squared tau 1, it fixes 2 and it interchanges 1 and 3. So that's tau 2. So sigma squared tau 1 is tau 2. What goes in here? This is tau 1, tau 1. So tau 1 fixes 1 and interchanges 2 and 3. So when you square tau 1 or multiply it by itself, 1 goes to 1 goes to 1, 2 goes to 3 goes back to 2, 3 goes to 2 goes back to 3. This is, again, the identity. So tau 1 times itself is the identity, and so on. So it's a good exercise and a very important exercise to calculate all the other entries in this table, the multiplication table for sigma 3. Let me just do one other calculation. I did sigma times tau 1. What about tau 1 times sigma? So tau 1 is 132. Sigma is 231. When I compose them, 1 goes to 2, goes to 3. 2 goes to 3, goes back to 2. 3 goes to 1, goes to 1. So this fixes 2. This is equal to tau 2. So tau 1 sigma is tau 2. And again, here you notice an instance of the following important fact. Sigma times tau 1 is equal to tau 3. Tau 1 times sigma is tau 2. They're different. So the order of multiplication matters. This just is another example of the fact that S3 is a non-abelian group.
Professor, question. So would it be abelian then if it were to be something else like S2, S4, S5?
I'm sorry, I don't understand your question. Please repeat it.
Since S3 is non-abelian, would it change to abelian if we were to change, S3 to S2 or S3 to S4 or S5?
Well, so Sn is non-abelian for all n greater than or equal to 3. So S1 is just consists of the identity. The identity times the identity is the identity. It's abelian. S2 just has 2 elements. It's abelian. But once you have permutations of a set with 3 or more elements, it is always non-abelian. Other questions? So a very special kind of permutation is called a cycle. A K cycle in Sn is a permutation. We write it in a special way, like this ordered sequence, A1 up to AK are distinct integers in the set from 1 up to n. And the way this permutation operates is as follows. A1 goes to A2 under sigma. A2 goes to A3. A3 goes to A4. A4 goes to A5. You keep going around this kind of circle till you get to A sub k minus 1. A sub k minus 1. A sub k minus 1 goes to A sub k. And AK goes back to A1. And if B is any element of the set of integers from 1 to n, and it's not one of these k elements, then sigma of B is equal to B. So this permutation moves these k elements from one to the next in this cycle, and everything else is fixed. So for example, suppose you had sigma equal to 2, 7, 3, 5 in S8. So this is a permutation which sends 2 to 7, 7 to 3, 3 to 5, and 5 back to 2, and everything else isn't moved. 1 goes to 1, 4 goes to 4, 6 goes to 6, 8 goes to 8. So if we wanted to write sigma in the standard form, as this 2 by 8 matrix, 1 goes to 1, 4 goes to 4, 6 goes to 6, 8 goes to 8, but 2 goes to 7, 7 goes to 3, 3 goes to 5, 5 goes back to 2. So this is the standard form for sigma, and this is the cyclic form. Okay. So a cycle is a special kind of permutation, which is easy to visualize. It's like you're going around a circle. And I showed on Monday the following theorem. Every permutation is a product. Product means product in the group, which means composition of functions. Every permutation is a product of disjoint cycles. So let's just recall the definition. If we have sigma 1 is the cycle A1 up to A sub k, and sigma 2, and all in Sn, and sigma 2 is the cycle B1 up to B sub L in Sn. So here we have k different numbers written in order. Here we have L different numbers are written in order. Sigma 1 and sigma 2 are disjoint if the numbers in this set are different from the numbers in this set. If AI is different from BJ, for all I going from 1 up to K, and all J going from 1 up to L. So that's what it means for cycles to be disjoint. And I also had proved that disjoint cycles commute. Right? Not all permutations commute because Sn's a non-abelian group. So if sigma 1 and sigma 2 are disjoint cycles, then sigma 1 times sigma 2 is equal to sigma 2 times sigma 1. So for disjoint cycles, the order in which you write them doesn't matter. And there is a simple calculation to decompose or represent every permutation as a product of disjoint cycles. So suppose I have a permutation in S9. See, 1, 2, 3, you need a 5 and a 6. So here's a permutation in S9. 1 goes to 4, 2 to 8, 3 to 5, 4 to 6, 5 to 2, and so forth. So if you look at this permutation, let's start, I can start anywhere. So maybe I'll start with 4, doesn't matter. I'll start with 1, but it really doesn't matter. 1 goes to 4. 4 goes to 6. 6 goes back to 1. So somehow in this permutation, there's this 3 cycle, 1 to 4, 4 to 6, 6 to 1. What about 2? 2 goes to 8. 8 goes to, oops, I missed something. 1, 2, 3, 4. Better make this a 9 because I didn't have a 9 here. So 1 to 4, 4 to 6, 6 to 1. 2 goes to 8. 8 goes to 5. 5 goes back to 2. See, I haven't used a 3 yet. 3 goes to 9. 9 goes to 7. 7 goes back to 3. So sigma, so this is a product of 3 disjoint 3 cycles. Okay. Any questions about this, how I got this?
Can you repeat how we get to 8, 5?
Okay, well, 2 goes to 8. 8 goes to 5. 5 goes back to 2. So 2 goes to 8, 8 goes to 5, 5 comes back to 2.
Thank you.
So let's take another example. Here's going to be a permutation, and that's 13. I'm just putting these numbers down at random. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay. So write this, right now you, not me, write this sigma as a product of disjoint cycles. So spend a minute or two doing that, and I will check off the attendance for whatever reason. Plumage. Miaui. Alba. Espinal. Tapsoba. Alberto. Santiago. Duran. Hernandez and Hernandez. Forch. Delbray. Sturgis. Sidibe. Sedano. Campos and Campos. Haynes, Cruz, Rodriguez, Sar, Gonzalez, Darame, Clark, Soto, Benitez, Shaduri, Ahmed, Headley, Yu, Nasser, and there's someone named Nil, N-I-L. What is your last name? Yeah. Nil, N-I-L. What is your last name, please?
Professor, he sent it in the chat.
Oh, Dar. So did you sign up late for the course? Because I don't have you on the roll that I have that I'm looking at right now. No. Okay, so here we have a permutation sigma. Can someone read off to me the cycle decomposition of this? What's the cycle that starts with 1? Can someone tell me?
5,
Yeah, go ahead.
9,
Yeah,
13, 8, 6, 10, 2, 12, 9, 9,
2, 12. 12 goes to, this is a 4.
okay, 4,
And then what's after 4?
1. That's it.
Right, okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is a 10 cycle, okay. And what's the next cycle?
2, 12,
Sorry?
9, 13, 8, 6, 10.
No, we already have that. So 9's already in this cycle. So you look for a number that hasn't been used yet. So for
Okay.
example, the first number that hasn't been used is 3. 3 goes to 7. 7
that's
goes
it.
back to 3. So this is a 2 cycle. And the only number that doesn't appear so far is 11. 11 goes to 11. So you could call that a one cycle, just means it goes to itself. Or what you usually do is you can write this or not write it. And you can just ignore it if you like, it doesn't matter. So someone just logged in as Galaxy 7 something, but it's useful to have a name. So if you want me to mark you present. Galaxy J7 Prime, whoever this is. What is your name, please?
Ivaris with Bravo.
How do you spell your last name?
OUE
Right,
DROGO.
Drago.
Yes.
Okay, very good. I got you. Thank you.
Thank you.
Okay. Any questions about this? Okay. Now, the simplest non-trivial cycle is a two cycle. This is a two cycle. It just interchanges two numbers and leaves everything else fixed. And a two cycle is called a transposition. And we have another decomposition theorem that says every cycle is a product of transpositions, but not necessarily disjoint. And so, because every permutation is a product of cycles and every cycle is a product of transpositions, every permutation is a product of transpositions. So I claim, for example, that if I take the cycle 1, 2, 3, 4, this is the same as the product of the transpositions 1, 4, 1, 3, 1, 2. So these aren't disjoint. The number 1, in fact, occurs in every one of them. But you'll notice this product on the right, 1 goes to 2, 2 goes to 2, 2 goes to 2. So 1 goes to 2. 2 goes to 1, 1 goes to 3, 3 goes to 3, so 2 ends up at 3. 3 goes to 3, 3 goes to 1, 1 goes to 4, so 3 goes to 4. This sends 4 to 4, 4 to 4, 4 to 1, so 4 goes back to 1. So we see this is a correct mathematical statement. And the general formula for writing a case cycle as a product of transpositions, again, there are many different ways to do it, But if you have a K cycle, this is always equal to the product. One way to do it, not the only way. You take A1 and write the transposition with A1 with each of the other K minus 1 numbers in the reverse order. So A1 AK, A1 AK minus 1, A1 A4, A1 A3, A1 A2. So this always works. So if you have the permutation 7, 9, 8, 2, 6, 1, this is 7, 1, 7, 6, 7, 2, 7, 8, 7, 9. Here we have a 6 cycle, and here we have 5 transpositions. Every K cycle can be written in at least one way. It's a product of K minus 1 transpositions. Okay. Any questions about permutations? So there are two important classes of non-abelian groups. The first is permutations, so the symmetric groups. Oh, I should also point out, why is the word symmetry used? So let's think of a triangle, an equilateral triangle. And I'm going to put it on this piece of paper. And this is position 1, position 2, position 3 on the paper. And I'll call this vertex 1, vertex 2, and vertex 3. Okay. Now I want to pick up the triangle and put it down in the same place. How can I do that? Well, I could just put it down in the same place, or I could rotate it by 120 degrees or 2 pi over 3 radians. If I rotate it, then this is 1, this is 2, this is 3. All right, I'm thinking of this triangle as being like a piece of cardboard with these numbers written on the corners, and I pick it up out of the paper and I put it back in the same physical space, but I can change it. I can rotate it or twist it or whatever. See, what else could I do? I could rotate it again. So then 1, 2, 3. I have this way. So these are all, you might call these symmetries of the triangle. These are operations you can perform on the triangle, and it doesn't change its appearance. You're moving it, but it still looks the same. But like here, I'm rotating it 120 degrees. Here, I'm rotating it again by 120 degrees. What else could I do? Well, I could pick up the triangle, flip it. So I'm interchanging 2 and 3. It's like I'm rotating it around this line, and I get this. So I'm fixing this vertex, but I'm flipping the triangle, keeping this vertex fixed. Or I could keep vertex 2 fixed and flip the triangle, so this becomes 3 and this becomes 1. And the other thing I can do, I can fix vertex 3 and reflect the triangle through this vertical line. I get my 2 here and my 1 here. So these are the symmetries of an equilateral triangle. And I can describe each of these symmetries by what happens to the vertices 1, 2, and 3. Like if I don't do anything, 1 is 1, 2 is 2, and 3 stays at 3. So this symmetry, I can say, well, 1 stays at 1, 2 stays at 2, and 3 stays at 3. In this symmetry, vertex 1 gets placed at position 2. Vertex 2 gets placed at position 3. Vertex 3 gets placed at position 1. In this symmetry, 1 gets put at position 3, 2 at position 1, and 3 at position 2. In this symmetry, 1 doesn't move, but 2 goes to position 3 and 3 goes to position 2. In this symmetry, 1 gets sent to 3, 2 is fixed, and 3 is sent back to 1. And in this last symmetry, 1 ends up at position 2, 2 ends up at position 1, and 3 hasn't moved. So this is writing these 6 symmetries, but as permutations, this is the identity, this is sigma squared, this is tau 1, this is tau 2, and this is tau 3. So you can see that S3, the symmetries of this triangle, are in one-to-one correspondence with the permutations in S3. And in fact, whenever you have a group, somewhere there's some geometrical object, and the elements of the group are describing symmetries of the object. So for S3, the object is an equilateral triangle, and the symmetries are all the ways you can lift the triangle off the paper, turn it, flip it, you can't cut it or stretch it, and then put it back in exactly the place it originally was, but the vertices could be in different positions. So one symmetry of a triangle is a rotation by 120 degrees. Another symmetry of a triangle is fixing a vertex and flipping the triangle without changing the position of this vertex, just 180-degree flip. And the symmetries of the triangle correspond one-to-one to the permutations in the symmetric group S3. So that's one reason why the symmetry is there. All right. Any questions about this? This is really very important because it gives a very nice connection between geometry and algebra in terms of the symmetries of geometrical objects. Okay. So the second group, the second class of non-abelian groups are matrix groups. And at this point, we're just going to consider the simplest case, 2 by 2 matrix groups. So a 2 by 2 matrix It's just a square array of numbers, A, B, C, D, written like that. This is a 2 by 2 matrix. And you can add matrices coordinate-wise, but then you just get a simple abelian group. What's more interesting is multiplication. And the set of 2 by 2 matrices, I'll call it M sub 2. It's this set. But the coordinates, the A, B, C, and D, they could be integers, they could be fractions, they could be real numbers, complex numbers. So let me just write M sub 2 of R. This is all matrices with the coordinates A, B, C, D in R. And depending, you could pick the integers, the rationals, the real numbers, the complex numbers, all sorts of things, right? So M2 of Z, for example, is all A, B, C, D with A, B, C, and D integers. All right. Matrix multiplication. I mean, if you have, in calculus, you probably learned the scalar product of the dot product of two vectors. If you had a vector AB, which I'll write as a row, and a vector EG, this is like a row into a times a column. This is defined to be AE plus BG. I mean, in calculus 3, you write this as the dot product of EF, and I write them both as rows. This is the same thing, AE plus BG. And this is the dot product that you see in calculus. And it's the same thing if I write one vector as a row and the other vector as a column, it's still AE plus BG. And if I'm going to multiply two matrices, two 2 by 2 matrices, the element that goes in the row I, column J position in the product is what you get by multiplying the ith row on the left with the jth column on the right. So this is row 1 and row 2. This is column 1, column 2. So in row 1, column 1, I take the first row times the first column, AE plus BG. For row 1, column 2, I take the first row times the second column, AF plus BH. Second row, first column, second row times first column, CE plus DG. Second row, second column, CF plus DH. So that's the definition of the product of two 2 by 2 matrices. So if I want to multiply 1, 2, 3, 4 by 5, 6, 7, 8, well, I'll let you do it. Do that calculation. So what is the first row of this matrix? Can someone tell me?
5, 12. Hello?
Yeah, go ahead.
On number 5 and number 12.
I'm sorry. What goes in here? First position?
5.
So this is 1 times 5 plus 2 times 7. So this is
Oh.
5 plus 14. So this is a 19. What goes in here? First row, second column.
22.
So it's 1 times 6 plus 2 times 8, and 6 plus 16 is 22. What goes in here? What are the numbers in the second row?
43.
Sorry, I just didn't hear.
43.
And here?
42.
Let's see. So here, second row, first column is 3 times 5 plus 4 times 7. That's 15 and 28, which is 43. Second row, second column is 3 times 6 plus 4 times 8. That's 18 plus 32 is 50.
That was 156.
Okay.
50.
Suppose you multiply in the opposite order. The matrix 5, 6, 7, 8 times the matrix 1, 2, 3, 4. So first row, first column, 5 plus 18 is 23. First row, second column is 10 plus 24 is 34. First row, second row, first column is 7 plus 24 is 31. And second row, second column is 14 plus 32 is 46. And you see, these are completely different. Which tells us right away that matrix multiplication is not commutative. Matrix multiplication is not commutative. So now it's an exercise. It takes a piece of paper to check that matrix multiplication is associative. So if you took A, B, C, D, and multiplied it by E, F, G, H, and you took that product with the matrix J, K, L, M, that would be the same as multiplying A, B, C, D times the product of E, F, G, H times J, K, L, M. So this is just a calculation which you have to do. There's also the identity matrix, what is called the 2 by 2 identity matrix. I is 1, 0, 0, 1. And you can check that you take the matrix ABCD times 1, 0, 1, you get ABCD. And if you take 1, 0, 0, 1 times ABCD, you get ABCD. So this matrix is the multiplicative identity. So if you look at 2 by 2 matrices, it doesn't matter whether the coefficients are integers or rational numbers, real or complex numbers. In all cases, the multiplication is not abelian, not commutative, but there is this identity. Now, there is a number associated to the matrix A, B, C, D, which is called the determinant, which is AD minus BC. And a very important fact about the determinant is if you have the matrix, if you have two matrices, A and B, 2 by 2 matrices, when you multiply them, you get a 2 by 2 matrix. And the determinant of the product is the product of the determinants. Again, this is a calculation. Maybe I'll do it just for fun. So if A is the matrix A, B, C, D, the determinant of A is AD minus BC. And if B is the determinant E, F, G, H, the determinant is EH minus FG. What is the matrix AB? When I multiply them, I get AE plus BG, AF plus BH, CE plus DG, CF plus DH. It's this 2 by 2 determinant, 2 by 2 matrix. What's the determinant of AB? Well, it's this times this minus this times this. Okay. Well, that looks like a mess, but it doesn't matter. We still have to figure it out. Let's just multiply. This is just high school algebra. So you distribute this across, whatever you call it, ACEF plus ADEH plus BCFG plus BDGH. That's what I get when I multiply these two expressions. Minus what I get when I multiply these two expressions. I get ACEF plus ADFG plus BCEH plus BDGH. So it's this minus this. And I do notice that these cancel and these cancel. So I have ADEH minus ADFG plus BCFG minus BCEH. If I factor an AD out of these first two terms, I get EH minus FG. If I factor a minus BC from these terms, I get EH minus FG, because minus times minus is plus. And if I factor out EH minus FG, I get AD minus BC, EH minus FG. That's the determinant of A times the determinant of B. So that's basically, it's a simple calculation, but it is a calculation, and you do have to know how to multiply, okay? Now, we've seen that matrix multiplication is associative. There's an identity. We would like to know if there's an inverse. And the answer is, for a 2 by 2 matrix, sometimes yes and sometimes no. So suppose you have A is the matrix A, B, C, D, and let's suppose that the determinant of A happens to be 1. In that case, suppose I let B be the matrix D minus B minus C A. All right? I just picked that for, it's a lucky guess if you like. So what is A times B? It's A, B, C, D times D minus B minus C A. When I multiply, I get AD minus BC, CD minus CD. See, first row, second column is minus AB plus AB and minus BC plus AD. And you notice these are 0 and AD minus BC is 1. So AB is the identity. And if you do the second calculation, you'll see that BA is also the identity, which means if the determinant of A is 1, then A is invertible. It has an inverse. And the inverse of A is D minus B minus CA. So you don't have to, well, this is it. So you just have to memorize that or write it down and, be able to look it up all the time. So what we proved is if we look at the set of matrices A, B, C, D, let's take a particular case where A, B, C, D are integers and AD minus BC equals 1, this is a group. And it's called, for whatever reason, SL subscript 2 of Z. So the L means linear, that's just another word for matrix. The 2 means the 2 by 2 matrices. The Z means the integers are, the coordinates are in Z, they're the integers. And the S means this is special. Special in the sense that these are matrices with a determinant 1. So this is stands for special linear group of 2 by 2 matrices. That's the SL, special linear. This is the special linear group of 2 by 2 matrices with integer coefficients. So for example, A equals this is an SL2Z because the determinant of A is AD minus BC is 1. And A inverse is you interchange these two elements, which they don't move, and you change the signs of the off-diagonal ones. Is this? And again, you can check that this is a 2 by 2 matrix with determinant 1, and if you multiply the two together, you get the identity. Here's another nice matrix, which is in SL2Z. Suppose T is the matrix 1, 1, 0, 1. That's pretty simple. So the determinant of T is 1 times 1 minus 0 times 1, which is 1. And T inverse is 1 minus 1, 0, 1. What happens if you multiply T with itself? One, 1, 0, 1 times 1, 1, 0, 1. So do that multiplication and tell me what you get. 1, 1, 0, 1 times 1, 1, 0, 1. What is the product of those two matrices?
I think it will be the same matrix, 1, 1, 0, 1.
Let's see. So row into column, 1 times 1. Let me just write this out. So this is 1 times 1 plus 1 times 0. 0 times 1 plus 1 times 0. What goes over here? 0 times 1 plus 1 times 1. What goes up here? First row, second column, 1 times 1 plus 1 times 1. 1 plus 1 is 2. Oh. So it's not the same. It's you have a 2 here instead of a 1. In general, suppose you have the matrix 1K, 0, 1 and the matrix 1L, 0, 1. Multiply them together and tell me what you get.
Professor, excuse me, how did we get the number 2?
Well, so this is the first row, second column. So I multiply the first row times the second column. 1 times 1 plus 1 times 1. Right? First row multiplied into the second column. 1 plus 1 is 2. And when you multiply these, what do you get? So the product of these two matrices, what is the first row? 1, K plus L, 0, 1. So in fact, we have something very nice about this matrix T. If T is 1, 0, if T is 1, 1, 0, 1, T to the K is 1K, 0, 1 for any K. And T to the K times T to the L is 1K plus L, 0, 1. So the powers of this matrix T are just like the integers. And when you multiply 2 powers of t, you're summing the exponents. That's what you get over there. And this is a very important matrix. It's in SL2. So the set of all powers of k, positive and negative and 0, is the same as the set of all matrices 1k, 0, 1 for k in Z. And you notice if you have t to the k times t to the minus k, that's 1k, 0, 1, 1 minus k, 0, 1. When you multiply them, the only thing that changes is the upper right-hand corner, and you get the sum, k minus k is 0. That's the identity. So the inverse of t to the k is t to the minus k, and the set of all the powers of t is a subgroup of the group SL2Z. Right? A subgroup of a group is a subset that contains the identity of the group, is closed under multiplication, and contains the inverse of each of its elements. Let's look at another example of a matrix in SL2Z. It'll be the matrix 0, minus 1, 1, 0. That's in SL2Z because the determinant of S is 0 times 0 minus this product minus 1 times 1, which is 0 plus 1 or 1. So this is a matrix in SL2Z. So you really have to become proficient at matrix multiplication. What is S squared? What do you get when you multiply this matrix by itself? Right. Do the calculation and let me know. So can someone tell me what we get?
Zero, 2.
Let's see. So in this position, you get 0 times 0 plus minus 1 times 1. That's minus 1. In this position, you get 0 times minus 1 plus minus 1 times 0, you get a 0. In this position, you get 1 times 0 plus 0 times 1. And in this position, you get minus 1 plus 0, which is minus 1. So S squared is the matrix minus 1, 0, 0, minus 1, which I could write as minus the identity, if you like. So let me just call this matrix minus I. So if I take this matrix in SL2Z and I square it, I get minus the identity. Minus 1, 0, 0, minus 1. So in the notes that are posted on Blackboard, there's a section on these groups of matrices, then you really should study it, because this is the second really important class of non-abelian groups. We have the symmetric groups and we have the matrix groups. Permutations and matrices, they're really, really important in algebra. And you have to be able to compute with these things and then be able to prove some simple theorems about them. That's the story. Okay, any questions about this? I mean, there's a fair amount to learn if you haven't seen permutations before, and if you haven't seen matrices before, then you need to spend a fair amount of time doing as many calculations as you are able to. Right? It's really important to get to know this. Okay. Any last questions before we go?
Professor, I have a question for the homework. Is this Friday?
Yes, there's a homework due this Friday.
Thank you, Professor.
It's homework 3. All right, all. Be back on Monday.
All right. Have a nice day.
All right,
Have a
thank you.
good day, Professor.
All right, you too. Bye, all.
Professor. Hello?
Yeah,
Okay,
Did
bye,
you get
Professor.
bye.
Thank you.
Professor, did you get my email I sent to you earlier?
I don't know. What did it say?
It was just if we could have office hours after class, if that's okay.
So you want to have an office hour right now, or do you mean like next Monday?
Oh, like right now, but if this isn't a good time, we can do it in some other time.
No, right now is fine. No problem.
Okay. Let me get my stuff. It was just to go over chapter 2 semi-groups. I'm having a hard time understanding them a bit. If we could go over some of the topics and have, I guess, some numerical examples to go along with them, maybe that'll clarify a few things for me.
So I'm not sure what you're asking, because a semigroup is just a set with a multiplication that's associative. So a semigroup is just a set with an associative multiplication or addition if you're writing the binary operation as. So there are, an infinite number of semigroups in the universe. And for example, if you take the set of all integers from 7 on, this is a semigroup under multiplication. Because if you multiply any two numbers in this set, you get another number in the set. And multiplication is associative. And it's also a semigroup under addition. Because if you add any two numbers in this set, you get another number in the set. All right, but I mean, what is it that exactly that you want to know? All the groups that we looked at are semigroups. Because a group is a set with a multiplication that's associative and also has an identity and inverses. But for a semigroup, you just have to have closure under the multiplication or under the group operation.
Let me see. Let me see what page it was of the notes. It was page 27. There was a corollary with a proof for Theorem 13.
Wait just 1 second. Let me see.
What's that?
So you have to read the theorem to me because I don't have the notes handy.
Okay. Wait, can I share my screen real quick?
Yeah, sure.
Okay. All right, share screen. Okay. Can you see the screen?
Yep.
Okay, so these two parts were a bit confusing right here. The corollary 1 and 2. So like, how do I? What is it asking me, and how would I do it with, like, I guess, numbers?
Well, there are no numbers. So, so move up to the theorem if you can.
Okay. All right, Theorem 13. Let's see where you're at. Well, this will be easier. Let me just do the find. Theorem 13. So that's 14. Let me go up a bit. So- let's see.
You just go up a page.
Up a page. Gotcha.
Yeah, I mean, it has to be right before the corollary. There you are. Okay. So theorem 13 says, okay, so let me go back to, so you can see my paper.
Okay. Let me exit. Okay.
All right. So in a so multiplication is a binary operation. So you can multiply two things. And if we want to define the product of n things, we define it inductively. So x1, x2, x3 is defined to be x1 times x2 times x3. And x1, x2, x3, x4 is defined to be x1, x2, x3 times x4, right? Which is, but x1, x2, x3 is this. This is x1, x2 times x3, all times x4. So this is, and in general, we define the product of n elements of the semigroup inductively, assuming you know what the product of n minus 1 elements is. The product of n is x1 up to x sub n minus 1 times xn. That's the definition. And we want to prove that if k plus L is equal to n, if I take the product of the first k elements times the product of the next L elements, right? So here you have k elements, and here you have n minus k, which is L. That's the same as what I defined as the product of n elements. So it's not obvious that this is true, right? There's a, if you take the product of k elements times the product of L elements, it's equal to this. So you have to think for a while, maybe just to understand that there's a problem here. It's not obvious why this is true. it requires a proof, and the proof is a little bit subtle. But this has nothing to do with numbers. I mean, you can't like plug in numbers and see what's going on. Except at the level of elementary school, where you might want to prove that 2 times 3 times 5 times 7 is the same as 2 times 3 times 5 times 7, right? So this is 6 and this is 35. And when you multiply them, you get 210. And here, this is 105 times 2. And when you multiply them, you get 210. And they're equal. So if you like, that's a numerical instance of what is being stated in the theorem. Right? That's what we're doing.
Okay. Okay. Yeah. No, that makes sense now.
Right. But it does take some thinking to understand even that there's something that needs to be proved in the first place.
Okay. Okay. Aside from that, can you go over, I guess, complex numbers in the way that we'll be using them in this class, I guess?
Well, I mean, complex numbers are complex numbers. So a complex number z is of the form x plus yi. And if you look at the ordinary plane, the point x comma y is the same as the complex number z equal x plus yi. So geometrically, a complex number is just a point in the plane. So, you know, I squared is -1. And, you know, if you add 2 complex numbers, you're just adding them. You're just adding them by coordinates, or real parts and imaginary parts. If you're, I mean, because this is 2 plus 3i plus 7 plus 8i is 2 plus 7 plus 3i plus 8i is 9 plus 11i. Oops, sorry, 9. Yeah, 9 plus 11i. And when you multiply, you just distribute across. This is 2 times 7 plus 2 times 8i plus 3i times 7 plus 3i times 8i. 2 times 7 is 14. 2 times 8i is 16i. 3 times 7i is 21i. 3 times 8i squared is 24i squared, but I squared is -1. So this is just -24. So you get -10 plus 37i. So, you know, just go anywhere on the internet and look up complex numbers, and you ought to know how to add, subtract, multiply, and divide them.
Okay, yeah, no, it's a bit clearer now, right?
If you can add and subtract and multiply real numbers, you can add and subtract and multiply complex numbers. The only thing that's tricky sometimes is how you divide. So if you have a complex number like 2 plus 3i, and you multiply it by 2 minus 3i, you can check, you get 13.
Okay. Yeah, no, I get it.
Yeah.
Okay,
I mean,
it's a bit clearer.
but again, you know, if you're not used to arithmetic with complex numbers, then just do some examples.
Okay, all right. Yeah, those were kind of the 2 topics that were a bit confusing. Can you clarify, Professor?
Sure. But,
All right.
you know, actually, I'm happy to stay after class, you know, like this, anytime you have questions. So that's no problem at all, usually.
All right, no. All right, good to know. All right, Professor, see you.
Okay, all right, bye. Anyone else have a question who's still here?